and comment somewhat on the implications of the real story for science. I should say that the biggest the biggest of these fables is probably the one about Galileo and the Catholic Church, right? Where the Catholic Church oppresses the pioneering scientist, and the scientist stands firm against this huge impersonal bureaucracy and the establishment trying to squelch him and so forth. The truth of that is actually very subtle and very interesting, and I can't go into it now, among other things, because I'm not a historian of science. I'm not the best person to talk about it. But check that out sometime. Anyway, for this particular set, this is the fable of the Ptolemaic epicycles, and the moral is that simple theories are better. And you particularly don't like theories which get more and more complicated the better and better your data become. I should say that the word simple in there turns out to have a technical meaning. If you take a statistics course, what I mean by simple is something that has relatively few free parameters. I'll just leave that at that. You can go talk to the statisticians about it. Okay, so if your theory is getting overwhelmed by epicycles, then you'd better go out and come up with some other better theory. And so people tried to do that. And the first step along the way was, of course, Copernicus. Copernicus, as you probably recall, decides that the geocentric model is wrong. Things ought to be heliocentric, the sun in the middle. So you put the sun in the middle, and everything, including the Earth, goes in circles around the sun. And this was revolutionary. And in fact, the title of the book he published was De Revolutionibus Orbium Celestrum, which means of the revolutions in the sense of revolving of the celestial spheres. And the use of that word, revolution, is one of the things that pushed the word revolution to its current meaning, meaning overthrowing authority in some ways. Originally, it just meant to revolve. But this was so revolutionary that people started to use the word in the other way. This wasn't actually as great a theory as you might think, because it still needed epicycles. Not as big, not as many, but it didn't get rid of the problem with epicycles. And that didn't work itself out until a generation or two later, when Kepler came along. Kepler was a famous astronomer, and he had in his possession, because he stole them, the best naked eye results that had ever been obtained of the motions of the planets, in particular Mars. And he described these motions in 3 laws of planetary motion. And you can look them all up in a textbook. In other kinds of courses, we would have you memorize these things. I'm not going to do that. The key point here is that these are not circles. They're ellipses around the sun. That, it turns out, gives you a model for planetary orbits which, when you take better and better data, doesn't change. They're still ellipses. You don't need little ellipses on top of these ellipses to explain everything that's going on. So this now has excellent descriptive power. It really describes what's going on, and when you make further observations, it still describes what's going on. It does not have any explanatory power, in the sense that if you say, why ellipses? Kepler had no idea. That's just the way God made it. So it's not, in any particular way, an explanation. For the explanation, you have to wait another generation or two until we get Newton. Newton writes down 3 laws of his own, but these are now 3 laws of motion, not planetary motion in particular. And again, one could write these down and memorize them and learn them, and that would be a good thing. Let me write down one of them. The second law looks like this. F equals ma, force equals mass times acceleration. And I write this one down simply to point out that that equation is the entire intellectual content of introductory physics for physics majors. If you go take Physics 180, this is all that they do. And they spend the whole time. It turns out you don't actually want acceleration. That doesn't tell you what you want to know. What you want to know is the trajectory, where the object is as a function of time. Those of you who have taken some calculus may recall that if you take the acceleration and you take an integral twice, you'd come up with position as a function of time. So here's what. So in the next 30 seconds, I'm going to explain Physics 180 to you. You substitute in some kind of a force, you divide by mass, you take two integrals, and that gives you the trajectory of the thing. That's all you need to know. Technically, of course, it's quite hard, but conceptually, pretty straightforward. And one of the things that Newton did with this equation was he took a particular force, namely the force of gravity, which he also wrote down a law of gravity. That tells you, for any given situation, what the force due to gravity is, substituted it in here, and figured out what the motions of the planets ought to be. And it turns out that he could derive Kepler's laws. He derives Kepler's laws. Very nice. Now, of course, in order to do this, he has to invent calculus. So it takes a little while. He was a great genius, but even so, inventing calculus from scratch, not something you want to attempt at home. And that was basically the start of both modern science and modern mathematics. So this marks the start of science in the following sense, that Newton has to make a couple assumptions along the way, sort of deep assumptions about how the world works. One is that the universe is governed by laws, and in fact by universal laws. And what I mean by universal in this sense is that they apply everywhere, that the same law of gravity that resulted in the top of my pen falling to the floor over there also is responsible for the orbits of the planets and the motions of the stars. This was a new idea. It's very familiar to us by now, but the idea that the planets ought to behave according to the same rules as stuff down here on Earth was a whole new concept. The other piece of the new concept is that these laws are mathematical in nature. This is why science is hard, because it's hard for human beings. I think it's something to do with the way our brains are wired to accept that this is true. It's very easy to imagine a world in which that's not true. Go read any fantasy novel. Any fantasy novel has a situation where the hero or the villain, by virtue of their strength of character, influences the events around them. So that is a rule governed by laws, perhaps, that are not mathematical in nature, but depend on the moral character of the individuals involved. Every human culture has such stories, including our own. It's very hard to get away from it. And the idea that, there's just this sort of mathematical structure and that your moral stature has no bearing on what's going to happen is kind of hard to accept. Fortunately, people turn out to be pretty good at math, so we can actually solve these problems and move forward. But these two ideas were revolutionary, and they are the basis pretty much of all science. Okay, so then Newton's laws get elaborated on for several centuries. By the end of the 19th century, things are starting to come apart a little bit. There are now problems that show up with Newtonian physics. It's been a big success on the whole, but there are now problems. And in the early 20th century, what happens is, two new laws of physics are invented. These are given the names quantum mechanics